All right, so in a semiconductor, there are two principal mechanisms by which charge carriers can move throughout the semiconductor medium, and they are drift and diffusion, okay? So we're gonna talk about drift first. So carrier drift occurs when an electric field acts on a charged particle. So these are what we would call Coulombic interactions. You guys covered Coulomb's law in 313 yet? Or you definitely had it in your physics 202 class and stuff like that anyway. So let's consider, instead of a semiconductor for right now, a big chunk of wire. Poorly attempting to draw a cylindrical cross section, right? So if this wire is made of metal, it should have just an absolute crazy amount of free electrons available for conduction, regardless of temperature. Right? When there's no electric field applied, the electrons should be moving about randomly, which is what I've tried to draw here. And they move randomly because of the Brownian motion, or the small amount of thermal energy stored in the electrons. If an electric field were applied, what would happen? They'll line up and all flow, well, not all of them, but most of them will flow generally in one direction, right? Where in the presence of an electric field, our drift current density, J drift, would be Q, the charge of an electron, times N, the electron concentration, times mu n, the electron mobility, times E, the electric field vector, okay? So for a wire where we only have a single charge carrier, this makes a lot of sense. What does this Q and mu n bit represent? Literally, it talks about it on Monday. Conductivity, right? So conductivity, what is the electric field? Just the voltage applied across the wire divided by the length of the wire, right? So we have current is equal to conductivity, or current density, so current per unit area, is equal to conductivity multiplied by volts over length. So this is just Ohm's law. Literally, Ohm's law for physicists, okay? Where that conductivity is just 1 over the resistivity, and then the area and the length bit take care of themselves for our generic equation. R is equal to rho L over A, all that kind of good stuff. So just Ohm's law, pretty neat in my opinion. The last two variables of our equation represent the drift velocity. For our charge carriers. So in a semiconductor material where both electrons and holes are present, we should observe a drift velocity of Vn is equal to negative mu n multiplied by our field vector E. And at drift velocity for holes, Vp is equal to positive mu p multiplied by our electric field vector E. Why is there a difference in signs? Pardon? That's one way to think about it, sure. So an electron has a negative charge, a charge of negative 1.60218 times 10 to the negative 19 coulombs, and a hole has a charge of positive 1.60218 times 10 to the negative 19 coulombs. I like to think of it as the way that the electric field interacts with the charge carrier, right? So electrons move in the direction opposite the field. So we need a negative sign. Holes, which are positively charged, move in the same direction as the field. And that has everything to do with Coulomb's law, right? So if we have an electric field oriented from left to right, it's going to want to attract electrons to the positive polarity terminal, whereas it's going to want to push holes away, right? So that's all that is there. So from this, the total drift current in a semiconductor under an electric field is simply J drift total is the electron drift plus the hole drift, or negative, I'm going to put Qn here. I'm being very specific because the charge of an electron is of the opposite sign of the charge of a hole. So Qn multiplied by n mu n E plus Qp multiplied by P mu P E. And we can group like terms together and exploit the fact that we have negative times negative, negative Qn, which is going to be negative times negative is just going to give us positive Q. So we're going to wind up with positive Q, the elementary charge, times, dang it, my screen moved on me, N mu sub N plus P mu sub P times E, where this guy right here, again, is simply sigma, our conductivity. So it's just charge times conductivity times electric field gives us our drift current density. What if we wanted to know the total current, not just the current density? What will we need to do? Multiply by the cross-sectional area of the medium it's traveling through, right? Because this current density is measured in amps per area. So we just multiply by the cross-sectional area. All right. So let's work an example problem. So let's say that I have a bar of semiconductor material, like so. I apply a voltage of 10 volts across my bar. My bar has a height of 1 centimeter. A width of 1 centimeter. And a length of 10 centimeters. We have an N-type crystal where there are 10 to the 15 dopant atoms per centimeter cube. And let's say, for the sake of argument, that our, sorry, I'm trying to look at where I wrote this down, or if I wrote it down, yeah. Our intrinsic carrier concentration, Ni, is 1.0 times 10 to the 10 centimeters to the minus 3. Let's say that our electron mobility, mu n, at this doping level is 1,250 centimeters squared per volt seconds. And our hole mobility at this particular doping level is 300 centimeters squared per volt seconds. And our goal is to determine the total drift current flowing through our crystal. Austin, do I need to re-say something? I see a little bit of confusion on your face and I'm worried it's my handwriting or something. You're good? Okay. All right. So this should be pretty fairly straightforward. We just had an equation that gives us everything that we need to know. And the only bits that we're actually missing here are the electron concentration and the hole concentration in our crystal. Once we have those guys, we're good to go, right? We know that J drift total is Q n mu n plus P mu P times E, right? Q is a constant, 1.6 times 10 to the negative 19 Coulomb, so that guy's taken care of. Mu n and mu p were given to us, so we don't need to do any work for those guys. So how do we get our electron concentration n based on the information that we're given? Right, from the number of donor atoms. So since ND is 100,000 times larger than Ni, we can say pretty easily that N is approximately equal to ND, or 10 to the 15 electrons per cubic centimeter, right? Neglecting the intrinsic electrons there doesn't really do anything because they're 0.00001 part of the total electron concentration. So throwing them away hurts nothing. Our hole concentration should be what? Approximately Ni squared over Nd, right? Because the mass action law says that our electron concentration multiplied by our hole concentration has to equal to Ni squared. So that's going to look like Ni squared over Nd, which is 1 times 10 to the 10 carriers per cubic centimeter, quantity squared, divided by 10 to the 15 dopants per cubic centimeter, gives us 1.0 times 10 to the 5. holes per cubic centimeter. So we now know Q, N, mu N, P, and UP. How do we get our electric field? Is it?
I believe it's the 10 volts that we're applying.
So 10 volts is an electric field, 10 volts is a voltage. How do we take that voltage information and determine the field strength? Divided by the length, exactly right. So 10 volts divided by which of those three dimensions? The 10 centimeters, absolutely right. All right, and so from this, our drift current is going to be 1.6 times 10 to the negative 19 coulombs multiplied by 10 to the 15 per centimeter cube, 1250 centimeters squared per volt second, plus 10 to the 5 centimeter cube, 300 centimeters squared per volt second, 1 volts per centimeter. And so if we throw this in our calculator, we should get 200 milliamps per centimeter squared. All right, I believe I made sure everything was given in centimeters so that all those areas and all that jazz would cancel each other out pretty easily. So centimeter to the -3 multiplied by centimeter squared gives us centimeter to the -1 divided by centimeter gives us per centimeter squared. So all that seems legit. The volts here cancels this voltage and this voltage. And so we wind up with coulombs per second, which is where those amps come from. So yeah, dimensionally, our calculator giving us 0.2, which is what it should give us, should be okay here. Now let me ask you guys a question. We actually, we did a little too much work here. Why? Exactly right. We could have neglected the contribution of the holes because they are 10 to the 10 or 10 billion, there are 10 billion times fewer holes than there are electrons in this particular crystal. So all of this math right here is effectively zero in comparison to what's going on over here. So we could have thrown away the whole contribution and it would have made no difference whatsoever, right? In an N-type crystal, it seems pretty reasonable that the electrons should dominate the drift current. Similarly, in a P-type crystal, it should be the holes that are dominating the drift current. All right, any questions on carrier drift? Hopefully pretty straightforward. Put a charged particle in an electric field. The electric field pushes on it, giving it or imparting it a particular velocity. Because we have moving charge, we have current, right? So now let's talk about diffusion, all right? Anybody know what diffusion is in general? Pardon? I can't hear, I'm sorry. High to low, an area of high concentration to an area of low concentration. Absolutely right. So let's say that I had some bad Taco Bell last night and I just ripped one up here on the stage. There will be a high concentration of fart particles here near me, and I hope a very low concentration of fart particles over there near Julie. But over time, because of that gradient in fart particle concentration, slowly the smell of rancid Taco Bell fart would make it to Julia. That is diffusion, okay? That's it, it's that simple, okay? So diffusion or carrier diffusion, I guess would be a better way to do it. Occurs when there are variations in the carrier concentration across a medium. When the concentration gradient occurs, by the way, could the people that are on Zoom type something in the chat so that I have a record that you're here? When a concentration gradient occurs, charge carriers tend to flow from a region of high concentration to low concentration. This is also Coulombic interactions, right? So if you have a bunch of electrons near each other, Coulomb's law tells us that they repel each other and want to spread out. Similarly, if we had a bunch of positively charged carriers all pushed close together, if we stopped holding them close together, the repulsive forces would cause them to spread. Okay. So diffusion is governed by what's called Fick's law. And the current density, J diffusion, will be Q multiplied by dn, a capital D, subscript n, dn of x with respect to x minus dp of x with respect to x. Okay. So capital Dn, capital D sub n, and capital D sub p are what are known as the diffusion coefficients or the diffusivities of electrons and holes in a semiconductor medium. This lowercase dn of x with respect to dx is simply the derivative of the electron concentration, represents the gradient, right? Same here, this dp by dx is the whole concentration gradient across the medium. Why is there a minus sign here for diffusion current density when there was a plus sign in the middle for holes? Or excuse me, for drift.
Because however many holes we have are going to slow down the diffusion. Because it's like if you had a vacuum and you release something into it, it would diffuse almost instantly. Whereas if you had something with a lot of particles in it, it would just naturally take longer.
I'm not sure what that has to do with the difference in the particles though. So think about, let's say that we have a crystal. Let me draw a picture here, which means I need to find out where I put my pen thing. So let's say that we have a crystal. Let's call this bit right here, x is equal to 0, and this bit right here, x is equal to L, okay? And we inject electron hole pairs into one side of the crystal, okay? So what I mean by that, let's say that we have an intrinsic crystal. So that this line right here represents N naught, which is the number of electrons at thermal equilibrium, and it also represents P naught, which will be the number or the concentration of holes at thermal equilibrium. I don't want to call them both Ni in this case because that would just be confusing, right? But so we have some kind of background level of both holes and electrons. Well, if we inject excess electron hole pairs into this system at one side simultaneously, then we will have like a local level. So let's call this N E and PE, the excess level. And we expect the carrier concentration to change across the crystal, okay? So effectively, this would be a situation where we are shining a laser or something like that on one part of a semiconductor crystal. And because of the good old Einstein and all that kind of good stuff, we're going to see that electron hole pairs are generated because of the photoelectric effect, right? But as we get further and further into the crystal, the light can't penetrate that far, so we should see that the carrier concentration gradually decays, right? And it's as a function of the optical properties of the crystal, all right? So in what direction are the electrons going to diffuse? Are they going to diffuse from left to right or from right to left? From left to right, because there's a lot more of them on the left side of the crystal than there are on the right side of the crystal. So the electrons diffuse this way, right? Which means the current due to the electrons is from right to left. Because good old Benjamin Franklin screwed it up way back in 1797 or whatever, right? What direction are the holes going to diffuse? In the exact same direction. So they're going to diffuse from left to right. What's the direction of the hole current? Also from left to right. So the negative sign here comes from the fact that even though the electrons and holes are diffusing in the same direction, the currents caused by that charge movement are in opposite directions. So the hole diffusion cancels out some portion of the electron diffusion or vice versa. Does that make sense? Okay. So let's say that the carrier concentration here N as a function of X is 10 to the 17 per centimeter cubed e to the negative X over LD, where LD is the mean free path for charge carriers in this particular crystal. What that means isn't particularly important to the problem, but that's effectively the average distance that a charge carrier can travel before it has a scattering event or something like that. So that's how long of a distance it has to accelerate before it typically tends to run into something that causes it to change direction. That's what mean free path means. Plus ND, and then PX is similar, 10 to the 17 centimeters per cubic centimeter, e to the negative x over LD plus NI squared over ND. So a similar situation where we're injecting electron hole pairs into the left-hand side of a crystal. But the difference in this particular problem is that our crystal is obviously doped N-type, so that we would see two different concentration states for intrinsic carriers here. But the math and all that kind of stuff is going to work out practically the same. So if dN is equal to 32.375 centimeters squared per second, dP is equal to 12.95 centimeters squared per second, and our mean free path in this case is 2,500 microns. Let's figure out what our diffusion current density should look like. Okay. So diffusion current density is Q dN dx minus dP dx. Well, we know what Q is. dN and dP were given to us. Capital DN, capital dP are diffusivities for our charge carriers. So really the only bits of information that we're missing are our gradients, right? So how do I figure out what dN by dx is? Yeah, I just take the derivative of n as a function of x. So how do I do that?
N of x, d of x are distribution rate, so ND is constant, that will drop out.
So when I take the derivative of n of x here, right? Yeah, because this is an exponential function plus a constant kind of background carrier concentration level. This part goes away because the derivative of it, derivative of the constant portion is 0. Similarly, the derivative of the background hole concentration will also get thrown away. So we really only have to worry about taking the derivative of the exponential bit. All right. So how do we take the derivative of an exponential function? Yeah, bring that part of negative 1 over LD out into the front. So we're going to have negative 1 over 0.25 centimeters, just so that my units are consistent, multiplied by 10 to the 17 per cubic centimeter, e to the negative x over our mean free path LD. Similarly, dP by dx, since we have the exact same concentration level, or the exact same exponential portion of the concentration level, we should get the same result there, right? So that's also going to be negative 1 over 0.25 centimeters times 10 to the 17 per cubic centimeter, e to the negative x over LD. And so from this, our diffusion current density is going to be 1.6 times 10 to the negative 19 coulombs times dn minus dp, right? Because the derivative bits are the same, so I can lump those together. And so I'll get, let's see, 32.375 centimeters squared per second minus 12.95 centimeters squared per second multiplied by that negative 1 over 0.25 centimeters, 10 to the 17 centimeters to the minus 3, e to the negative x over LD. And multiplying the bits out, I get a current density of negative 1.243 e to the negative x over LD amps per centimeter squared. So the current is in the negative x direction because the diffusivity of electrons is larger than that of holes. So even though there are more, excuse me, even though there are just as many electrons and holes being injected into the system, the electrons diffuse more easily and therefore contribute to the current more. Make sense? Everybody okay with that? All right. So the last thing that I want to talk about today will literally take 5-minute stops, and that is the Einstein relationship. So while carrier drift and carrier diffusion occur for completely and utterly different reasons, right? One has to do with the presence of an electric field pushing charge carriers about. The other one has to do with a concentration gradient that makes the charge carriers want to get away from each other. They are related. So the relationship is as follows. The ratio of the diffusivity of electrons to the mobility of electrons is equal to Boltzmann's constant times temperature divided by charge. And for holes, it's the diffusivity of holes divided by the mobility of holes is equal to that same ratio, kBT over Q. All right. And these guys are called, these relationships are called the Einstein relation. All right. This quantity kBT over Q also has a special name. It's not going to mean a whole heck of a lot to us right now, but we will see it arise over and over and over again when we start dealing with PN junctions and bipolar junction transistors and all that kind of good stuff. So let's call this VT, which is the thermal voltage. And it is approximately equal to 26 millivolts at T is equal to 300K. I think it's 25.94 or something like that. 26 is good enough for me. Okay. So this thermal voltage effectively represents the potential energy of an electron at a temperature of 300 degrees Kelvin. That's how much wiggle room it has. Okay. All right. So that's enough out of me for today. So we're wrapping up about, I guess, half an hour early. Sure, nobody has a problem with that for the first Friday of the quarter. Logan, what's up?
So since that VT obviously is temperature dependent, is that why circuits will fail when they overheat?
Circuits fail when they overheat for a variety of reasons, some of which we'll talk, well, we'll talk about what's called reverse bias breakdown when we start talking about reverse bias PN junctions. But when something breaks down, when an electrical component breaks down because it overheats, it largely has to do with the fact that, so as we give an electron more thermal energy, it starts to move faster and faster, right? So if we heat up an electron, we are essentially imparting kinetic energy. And when those electrons have enough kinetic energy, they can start to do things that they weren't supposed to do inside of that electrical component. So they reach a speed called ballistic transport, to where they actually start like punching holes through insulators and stuff like that. Like they're traveling so fast, they bury themselves inside silicon crystal, leaving behind holes and making it easier for conduction to occur. So when you have something passing a whole bunch of electrons that it wasn't designed to do, ohmic losses cause the temperature to ramp up even more. And so you have a thermal avalanche, effectively. So you start seeing more and more electrons generating more and more heat, and it just cascades and causes the device to fail. So that's a better explanation of why overheating components burn out, is because the first one that overheats makes it, the first electron, the first hot carrier makes it easier for the second hot carrier to do some damage, which makes it easier with the third hot carrier, and so forth and so forth. And it just snowballs from there. All right, any other questions? Yes, sir, Grayson.
The constant distribution of D and D, those be given to us? We have to figure out how to calculate those.
So for a homework problem or something like that, I'm either going to give you D, the diffusivity, or mu, the mobility. And then once you know one, you know the other because of Einstein's relationship. But I'm not going to make you go out of your way to like calculate one of those things without just giving you the other. So this is the level of difficulty. I'm not going to say, okay, so the whole mobility, which is dependent on temperature and 5 other things, is this. So look up, 8 different things from tables and figure out what you think the mobility is supposed to be. No, you're not graduate students. I'm not going to punish you like that. So this is the level of difficulty of converting between the two that I expect of you. And in fact, you have a homework problem number 5 is literally a table where sometimes I give you diffusivity and want mobility, other times I give you mobility and want diffusivity, and you literally just manipulate this trivial equation to get the answers.